Today we're looking at the June 2016 K Pure Math Paper 2 exam. So we begin with question 1. Let f of x equal 2x cubed minus x squared plus px plus q, given that x plus 3 is a factor of f of x. So let's pause here. So x plus 3 is a factor of x, so by the factor theorem, f of minus 3 should be equal to 0. Also, we are told that there's a remainder of 10 when f of x is divided by x minus 1. So dividing by x minus 1 gives a remainder of 10, which means f of minus 1 is equal to the remainder, which is 10, by the remainder theorem. So notice, now we're dividing by x plus 3, the remainder is 0, meaning x plus 3 is a factor. Alright, let's substitute. We're asked to find the value of p and q, so we should end up with a pair of simultaneous equations. So here's f of x. We're going to replace x with minus 3, so 2 into minus 3 cubed minus, replacing x with minus 3, so minus 3 squared, replacing x with minus 3, so minus 3p plus q equals 0. Let me just separate that. So minus 3 to the power of 3, that's negative 27 times 2, so that's minus 54, minus positive 9, so minus plus 9, that's minus 9, minus 3p plus q equals 0. So I believe we can group the constants. So we can group the constants on the right hand side here. So we have minus 3p plus q equal to 54 plus 9. And 54 plus 9, that's 63. That's 63 minus 3p plus q. And we are also told that the remainder is 10 when divided by x plus 1, which means f of minus 1 equal to 10. So now we're going to replace x with minus 10 over here. So we end up with 2 times minus 1 cubed minus 1 square, and p times minus 1, that's minus p plus q equal to 10. So minus 1 to add power, we end with minus 1 times 2, that's minus 2, minus positive 1, that's minus 1, minus p plus q equal to 10. So again, we can group the constants on the right, so we end up with minus p plus q equal to 10. We group these on the right hand side, so it's plus 2 plus 1. So we end up with minus p plus q equal to 13. 10 plus 2 plus 1. So notice we have a pair of simultaneous equation here. And these two. Alright, let me call this equation 1. Let me call this equation 2. So notice both of them have a q, so we can solve using elimination method, and so we can subtract. So we have minus 3, let me rewrite it, minus 3 plus q equal to 63. Restating equation 2, we have minus p plus q equal to 13. Alright, and then we can subtract term above, subtract term below, so that's minus 3p minus p. So this becomes minus 3p plus 1p, which is negative 2p. Q take away q, that's 0. 63 take away 13, that's 50. So we can divide both sides by minus 2. So minus 2 into itself, that's 1. So 1p, 50 divided by minus 2, that's minus 25. So p is minus 25, and we can substitute the value of p into equation 2 to end up with the q, to end up with the value of q. So notice we have minus p plus q equal to 13. If I transpose a q, I'll get q equal to 13 plus p. Right, so I group everything on the right hand side here except the q. So q equal to 13 plus negative 25. That's 13 minus 25. Value of p is negative 25. So 13 minus 25. So q is equal to minus 12. Okay, as we continue. Hence, solve the equation f of x is equal to 0. Let's remind ourselves what f of x was. F of x, that's 2x cubed minus x squared plus px plus q. So we can restate that, except that we're going to substitute the values of p and q respectively. Remember, p is minus 25, q is minus 12. So let's write down f of x. Okay, so that's f of x when we substitute the values of p and q respectively. Now we know that, we are told that, just recall that x plus 3 is a factor. So we can use long division or synthetic division to get the other factors. Let me use long division. Alright, so x plus 3, we're going to divide it into f of x. And we should end up with the other factors. So x into 2x cubed, that's 2x squared. We take the 2x squared, multiply it back to the divisor, so 2x squared times x, that's 2x cubed, and 2x squared times positive 3, that's 6x squared. And we subtract term above, subtract term below. So 2x cubed, take away itself, that's 0, minus x squared, minus 6x squared, that's minus 7x squared. We bring down the minus 25x. So we try and have two terms here before we try dividing again. So divide again by x. So x into negative 7x squared, that's negative 7x. We'll take the minus 7x, multiply it to the divisor here, x plus 3. So minus 7x times x, that's minus 7x squared. And minus 7x times positive 3, that's minus 21x. And we subtract term above, subtract term below, so minus 7x squared, minus 7x squared, end up with minus 7. Double negative gives a positive, so that's minus 7x squared plus 7x squared, which is 0. And then we have minus 25x minus 21x, so it's minus 25x plus 21x, that's minus 4x. Bring down this minus 12. Again, try and have two terms before we divide. So x into minus 4x, that's minus 4. Now we take the minus 4, multiply it with x plus 3. We end up with minus 4x minus 12. And we subtract term above, subtract term below. So minus 4x minus minus 4x. Double negative give us plus 4x, so that's 0. Likewise, minus 12 minus minus 12, that's minus 12 plus 12. We end up with 0, which we expect since x plus 3 is a factor, so we expect the remainder to be 0 when divided by x plus 3. So we know 2x squared minus 7x minus 4 is a factor, so we can rewrite the function as so x minus 3 times that is equal to the function. So we know there's a similar example of a function 12. And if I say to you 3 into 12 goes 4, it means 3 times 4 should give you 12 there. Right? In the same way, x plus 3 times 2x squared minus 7x minus 4 should give us the function there that we divided, right? So therefore the function solving f of x equals 0 is equivalent to solving x plus 3 times what we have up here, 2x squared minus 7x minus 4. And we realize now in this second bracket here's a quadratic. We can factorize that even further. So x plus 3. Let me factorize this quadratic using the AC method. Notice AC, 2 times minus 4, that's minus 8. So we need two numbers that multiply to give negative 8 and add to give, put a different color, and add to give minus 7. So these two numbers would be what now? Minus 8 and positive 1, right? These two numbers multiply to give AC, which is minus 8, and add to give the middle term here minus 7. So we can rewrite this as 2x squared minus 8x plus 1x minus 4. If we factor by groups, we end up with 2x into x minus 4, and same here, factor out 1 into x minus 4. So the factors would be x minus 4 and 2x plus 1. So factoring the second bracket there, we should end up with x minus 4 and 2x plus 1. And solving by factorization, we equate each factor to 0 and solve. So we have x plus 3 equals 0. We can equate x minus 4 to 0. Also 2x plus 1 to 0. Solving each of them. Subtract 3 from both sides. X equal minus 3 here. Add 4 to both sides. X equal to 4 here. Subtract 1 from both sides and divide by 2. We end up with x equal to minus a half. So those are our solutions for f of x equal to 0. Next, we're asked to use mathematical induction to prove that 6 to the power of n minus 1 is divisible by 5 for all natural numbers n. So proof by induction, 3 major steps. We need to show that the statement is true when n equal to 1. So we're going to show statement is true when n is equal to 1. Alright, so what statement? That 6 to the power of n minus 1 is divisible by 5. So when n equal to 1, 6 to the n minus 1 becomes 6 to the 1, replacing n with 1, minus 1. 6 to the power of 1 is 6 to the power of 1 is 1, is 6, sorry. So 6 minus 1 is equal to 5, and obviously 5 is divisible by 5. Therefore, the statement is true when n is equal to 1. Step 2, we need to assume. So let's assume the statement is true for when n is equal to k. So this was statement 6 to the power of n minus 1. So this time we're going to replace n with k. So this means that 6 to the power of k minus 1. We want to assume that this is divisible by 5, which means 6 to the power of k minus 1. If divisible by 5, it can be expressed as 5 to some natural number. Let's call this natural number p. And let me define p, where p is some natural number. Alright? So notice any natural number, once that number can be divided by 5, the number can be written as 5 times a value. For example, 15, we know 15 is divisible by 5. 15 can be expressed as 5 times 3. So think of any number you know that can be divided by 5. That number can be expressed as 5 times a natural number. We call that number P. Where P can be anything, any natural number that is, right? And then, so that's an assumption. And step 3, we're going to show that the statement is true. The statement is true when n equal to the number that follows k. Let's call that number k plus 1. Alright? So k plus 1 would comes after k, just as how 7, which is 6 plus 1, comes after 6. Alright, so this time we're going to replace, so this is a statement, we're going to replace now n with k plus 1. So therefore 6 to the power of k plus 1. No, 6 to the power of k plus 1 minus 1. What is it? Is it divisible by 5? Let's see. We can rewrite 6 to the power of k plus 1 as 6 to the power of k times 6 to the power of 1. And that's directly from the law of indices. Notice this is rewritten as 6 times 6 to the power of k. Alright, law of indices, same basics. If you add the powers, you end up with 6 to the power of k plus 1. Now, from step 2, we can do some transposing here. From step 2, if you look at step 2, 6 to the power of k, if you add 1 to both sides, here in step 2, 6 to the power of k is actually equal to 5p plus 1. So 6 to the power of k, we are going to replace 6 to the power of k with 5p plus 1. So you end up with 5p plus 1. And now remember we have 6 to the power of 1 outside here, which is minus 1. Let's expand our bracket. So 6 times 5p, that's 30p. 6 times 1, that's 6. And we have minus 1 outside here. So 6 minus 1, that's 5. So we have 30p plus 5. And we can notice 5 is a common factor, so we can factor 5. So 5, factor 5, we end up with 6p plus 1. Now, remember that p is a natural number. So if you multiply a natural number by 6 and you add 1, you end up with another natural number. So we can write this as 5 times some natural number. Let's call that number W. And let's define W, where W is equal to 6p plus 1. I could have used any letter or symbol to represent 6p plus 1. The point of the matter is that 6 to the power of k plus 1 can be expressed as 5 times a value, a natural number. And of course it's also a natural number. Which means that 6 to the power of k plus 1 is divisible by 5. So therefore, true for n equal to k plus 1. Hence the statement is true. So therefore the statement is true for all natural numbers. Natural numbers, which we call n. Alright, so let's move on. So given that P and Q are two propositions, complete the truth table below. Alright, so we have the implication, we have the conditional or implication, we have the or and we have the and we should know all of these tables. The implication or the conditional statement here, P imply Q, we know it's all true except for the true false. So true false, this one is false. The rest of them should be true. And PRQ, the only time we have false is when both of them are false. The rest should be true. P and Q, the only time we have true is when both of them are true, so true, and the rest should be false. And the final one, we're combining the fourth and the fifth column, these using the conditional PRQ imply P and Q. And again, the only time we have false is the true false. Notice we have a true false here, so this should be false. We have a true false here, this should be false. And the rest, true and true, should give us true implied true should give us true. This should also be true. State, given a reason for your response, whether the following statements are logically equivalent. So statements are logically equivalent if the truth values are identical. If the truth values are the same. So notice, these, the truth, notice P imply Q. That's that. And these, so notice the truth values here. This is true, false, true, true. This is true, false, false, false. So these statements are not logically equivalent. Not logically equivalent. Alright, since the truth values are not the same. Since the truth values are different. Alright? Truth values are different, or not the same. Or also could say they are not identical, whatever, anything equivalent to that. Alright, solve the following equation. Notice both of them are base 2, so we can use the law that says log A plus log B, and we can combine both logs by multiplying, by taking the product of A and B. So here we have log. Once we have in plus, we can combine both logs by taking the product. So we multiply these two. So this would be like the A, this would be like the B. So A times B or B times A, whatever. So it's x times 10, that's 10x, and x times minus x, that's minus x squared. Alright, so we combine both logs there and on the left hand side. And the laws of logarithm, whatever is in the bracket, so 10x minus x squared, according to the laws of logarithm. So 2 to the power of the power over here, so 2 to the power of 4 should give us what's in the bracket there. And of course, 2 to the power of 4, that's 16. We have 10x minus x squared. So we can group everything on one side since we have a quadratic. So we can, let me group everything on the right hand side. So we have x squared minus 10x plus 16. So we can solve this by factorization or the formula or whatever. How can we? So we need to factorize, let me use the AC method. We need two numbers that add to give negative 10 and multiply to give positive 16. Those should be easy. It's minus 8 and minus 2. So we rewrite negative 10x as minus 8x minus 2x. And we factor by a group. So we have x into x minus 8. And the other group, other pair of terms here, we have minus 2 as a common factor into x minus 8. So we have a common bracket, common factor, x minus 8, x minus 2 outside. Equate both factors to 0. So x minus 8 equal to 0, or x minus 2 equal to 0, which means x equal to 8, or x equal to 2. Next, a function f is defined as f of x equal x plus 3 over x minus 1, and obviously x cannot be 1 because if x is 1, you'll have a denominator of 0, and we know dividing by 0 makes the function undefined, so x cannot be 1. So we are asked to determine whether f is bijective, and bijective means it's both injective and surjective. Injective is what we call one-to-one. So let's test for one-to-one or injectiveness. So let's test for testing for testing for one-to-one. Same thing we call injectiveness, right? So testing for injectiveness, and for it to be injective, we'll let f of a equal f of b. Now, if the function is injective, a should be equal to b. Alright? If a is not equal to b, then it's not injective. Alright, let's see if a is equal to b. So f of a mean I replace all the x variables with a. So x plus 3 becomes a plus 3 over a minus 1. And f of b, replacing x with b this time, so that's b plus 3 over b minus 1. What can we do now? Let's cross multiply and see what happens. We cross multiply, just alright, we end up with a plus 3 times b minus 1, and we end up with a minus 1 times b plus 3. Let's expand group-like terms and simplify. Alright, so a times a, that's a times b, sorry, that's ab. A times minus 1, that's minus a. 3 times b, that's positive 3b. 3 times minus 1, that's minus 3. On the other side, a times b, that's ab. A times 3, that's 3a. Next, negative 1 times b, that's negative b. Negative 1 times 3, that's negative 3. Alright, so what we can do is notice if we add 3 to both sides, then this will cancel that. Alright, what can we do? Again, we can subtract AB from both sides. Notice we have my AB here, so we can subtract AB from both sides. So that will eliminate that. Any other like terms? Alright, so we can group the A's. We're left with minus A plus 3B equal to 3A minus B. So let me group the B's on the left hand side. So here we have 3B. So now 3b plus b. And if I group the a's on the other side, I would have 3a plus a, which leaves me with 4b equal to 4a. And we obviously can divide both sides by 4. So we end up with b is equal to a, or a is equal to b. So therefore, the function is one-to-one. Therefore, the function f is one-to-one. 1-to-1. And 1-to-1 is the same thing we call injective, right? Let's test now if the function is onto. Now, if the function is onto, let me just do that over here. If the function is onto, or what we call surjective, if is onto, alright, same thing we call surjective, then f of x should be equal to y. So now here's a function. We need to find f of x. We need to find x, alright? So f of x, so let me just do this up here, just for space. So we're going to do it up here. I'm going to let y be equal to x plus 3 over x minus 1. And I'm going to transpose for x. Alright, so I can put this over 1 and I can cross multiply again. So multiply, I'll end up with x plus 3, 1 times x plus 3 is equal to y times x minus 1. Expand and end up with x plus 3 equal to yx, same y times x, which is xy. Y times minus 1, that's minus 1. Alright, and so let me group all the x terms together now. So, group all the x terms together. So what will I have? Continue up here. I'll have now, let me just group the y terms over here. So 3, let me bring over as negative y. So I'll have 3 plus y, or y plus 3, doesn't make a difference. Equal to, group the x's over here. So end up with xy minus x, and minus x is same as minus 1x. And if I factor out the x, I'll have y minus 1 here. 3 plus y, let me call it y plus 3. Put the y at the front. Divide both sides by y minus 1. Alright, so x is equal to y plus 3 over y minus 1. So, alright, so we want to show that f of x is equal to y. Now, f of x is the same as f of y plus 3 over y minus 1. It's our substitution. So we're going to find f of y plus 3 over y minus 1. And it should be equal to y. Alright, so f of what's in the bracket here. So again, come back to here, this function here. We're going to replace x with whatever is inside of the bracket. So x plus 3 becomes y plus 3 over y minus 1 plus 3. Alright, so all I did here is replace the x in the numerator with y plus 3 over y minus 1. Likewise, in the denominator, x minus 1, again, we're going to replace x with y plus 3 over y minus 1. Minus 1. So, we have a lot to simplify here. Let's go ahead and simplify this now. Alright, so now we need a common denominator here. So I'll put 3 over 1 here. We need a common denominator of y minus 1 before we can add the two fractions here. So I'm going to equivalent fraction, y minus 1 and y minus 1. Alright, likewise down here, again we need a common denominator. So I'm going to multiply that by y minus 1, y minus 1. Alright. So at the top there, notice we have a common denominator there of y minus 1. So we can put the numerators together. At the top here, this numerator here is y plus 3. And the other one is 3 times y minus 1, which is 3y minus 3. Divide by, down here now, again, common denominator, y minus 1. And what's in the numerator now? Y plus 3 and minus 1 times y, that's minus y, and minus 1 times minus 1, that's positive 1. Alright, so we end up with, top here, we end up with, that's what? 4y, that's 4y over y minus 1. Divide by what we have down here now is y minus y, that's 0, 3 plus 1, 4. So that's 4 over y minus 1. So this becomes 4y over y minus 1 times y minus 1 over 4. Now y minus 1 into itself was 1. And 4 into 4y give us left with just y. So we have proven that f of x is equal to y. So therefore, f is onto. So the function is both one-to-one, which is injective. It's also onto, which is what we call surjective. Alright? So therefore, we can conclude, therefore, f is bijective. Alright? Since f is both one-to-one and onto. So it's both injective and surjective, hence it is bijective. So part C, let the roots of the equation, cubic equation here, 2x cubed minus 5x squared plus 4x plus 6 equal to 0. So we are asked to let the roots be alpha, beta, and gamma. State the values of the sum of the roots, which is alpha plus beta plus gamma, and the sum of the roots is actually negative b. So let's call this a, b, c, and the constant d here, 6. So the sum, that's the sum of the roots, that's negative b over a. The sum of the products, that's alpha beta plus alpha gamma plus beta gamma, that's c over a. And the product of the roots, alpha beta gamma, that's d over a. So the sum, negative b over a. Now b is negative 5 and a is 2, so it's negative 5, so it's minus 5 over 2. That's positive 5 over 2. So this means that that's alpha plus beta plus gamma, that's 5 over 2. And the sum of the products here, that's alpha beta plus alpha gamma plus beta gamma. C is 4, so 4 divided by 2, that's 2. And then the product, alpha times beta times gamma, that's I made an error here, this will be negative d over a, sorry, this will be negative d over a. Now d is 6, so negative d, that's negative 6 divided by 2, that's minus 3. Alright? So that's part C, part 1. C, that's part 2. Part 2. Hence or otherwise, determine an equation with integer coefficients which has roots 1 over alpha squared, 1 over beta squared, and 1 over gamma squared. So we first need the sum. Let's get the sum. So, alright, so the sum here would be, so we need the sum, so it would be 1 over alpha squared plus 1 over beta squared plus 1 over gamma squared. We need a common denominator. The common denominator would be alpha squared, beta squared, and gamma squared. No, this denominator, how can I make it alpha squared, beta squared, gamma squared? I would need to multiply this by beta squared and gamma squared, which would mean I need to do the same thing to the numerator, multiply by beta squared, gamma squared. Likewise, to get this to have the same denominator, I would need to multiply by alpha squared times gamma squared. So I multiply the top, alpha squared times gamma squared, and then this one I need to multiply by beta squared times gamma squared. It's the same here, multiply the top by beta squared times gamma squared, and I have the same denominator, so I can put the numerators together. Beta squared times gamma squared plus alpha squared times gamma squared. I think I made an error here. if you recall, this was beta square. This was beta square. I need to have the same denominator. So we need to multiply by alpha square times gamma square. So sorry, this was gamma square, sorry, my bad. It was gamma square. It was gamma square. So I need to multiply by alpha square beta square. So I need to multiply by alpha square times beta square, which I need to multiply the top also by alpha square times beta square. So this is plus the numerator alpha square times beta square. Alright, so notice we are told now that, what are we told now? We are told that this alpha square beta square plus alpha square gamma square plus beta square gamma square, which is what we have in the numerator, is equal to what we have over there. So this, we can replace the numerator with alpha beta, sum of the products, plus alpha gamma plus beta gamma all square minus 2 alpha beta gamma into alpha plus beta plus gamma all over, let me write this as alpha beta gamma, let me write it like this, all square. Now some stuff we have here now, so we know that this sum of the product here, the sum of the products here, we have that already. The sum of the products, we have that to be, where was it? We have that up here to be, the sum of the products, we have that here to be positive 2. The sum was 5 over 2. The product was minus 3. So, alright, so we have the sum of the products to be positive 2. Alright, so that's positive 2. So positive 2 square. The product, what was the product again? The product was negative 3 and the sum was 5 over 2. So the product was negative 3 and the sum was 5 over 2. So the product was negative 3, so negative 2 times negative 3 and the sum was 5 over 2. In the denominator, the product was negative 3, so negative 3 squared. Alright, so let's simplify this. So we end up with 4, and this is 1 over minus, this is positive 6 times 5 over 2. What's 6 times 5 over 2? 6 times 5 over 2, that's 15. So that's positive 15. Double negative here, gives us positive 6. Over 3 squared, that's what? 9. So that's 19 over 9. Alright, next we can find the product of the roots. So the product, of course, what were the roots? 1 over alpha square times 1 over beta square times 1 over gamma square. I think we found that already. Alright, so that's 1 over alpha square times beta square times the gamma square. We can rewrite this as 1 over alpha beta gamma all square. Good. Which is 1 over minus 3. Let's remember the product was negative 3. Alpha beta gamma came to negative 3. So 1 over negative 3 squared, which is 1 over 9. Also, we need the sum of the products. Alright, so out of space. We also need the sum of the products. Where can I put that now? The sum of the products. Let me put that up here. So we also need the sum of the products. The sum of the products. And here are the roots. So So the product, so that's 1 over alpha square times 1 over beta square plus 1 over alpha square times 1 over gamma square plus 1 over beta square times 1 over gamma square. And again, we can try to bring everything under one common denominator. We can make this common denominator be alpha square, beta square, gamma square. Alright now, for this to be, so we need a gamma square below here, gamma square. So we have to multiply the top also by a gamma square. Alright, so this will be gamma square at the top. Plus this, we need a beta square. So multiply denominator by beta square, but for the fraction to remain equivalent, we also have to multiply the numerator by beta square. And likewise, here we need what? Alpha square. So we need to multiply the top by alpha square also. Alright, so plus alpha square. So we can simplify the expression like that. And then now we can do some little rewriting. So now in the denominator now, we have what now? Alpha beta gamma square, and we have that already. I think that was 9. That was 9. And look, if you look at the question, we are told that here we are told that alpha square plus beta square plus gamma square is here is alpha plus beta. So this, notice the numerator, alpha square plus beta square plus gamma square is a numerator, is equal to all of this. Is a sum, and again we already have the sum. The sum square, and remember the sum was, what was the sum? The sum was negative, was 5 over 2. Alright, so we have a sum, the sum square, which was 5 over 2 square, minus 2 times the product of minus 2 times the product, the sum of the product, sorry. And again, that was 2. Alright? That was 2. So this become minus 2 times 2 there in the bracket. Substitution. And again, the denominator here it's out already to be 9. So I'll just replace it with 9. Same some cramps for space. So this was 9. Alright. So we end up with 5 over 2 square. That's 25 over 4 minus 4. That's 25 over 4 minus 4. Over 9. Alright. And 25 over 4 minus 4. That's 25 divided by 4. 4 into 6 minus that. So what we can do is write the 4 as 16 over 4. So that's 25 over 4 minus 16 over 4 divided by 9. So 25 over 4 minus 25 minus 16, that's 9. That's 9 over 4 divided by 9. Now dividing by 9 is same as multiplying by 1/9. Alright, so we end up with a quarter. Alright, so for this new equation, we have the product, we have the sum, we have the sum of the products. Alright? So we can formulate the equation. Alright, in this question we can formulate the equation. So water space. We put the equation here. So therefore, equation is x cubed minus, and then we always a sum now, minus, we have a sum here, 19 over 9 times x squared plus the sum of the products, which we had got to be a quarter, x minus the product. We calculate the product. The product was 19, so minus the product, which was 19. Alright, equal to 0, and of course we can multiply now. The LCM of 4 and 9 is 36, so we can multiply each term by 36. Put it in already, just to messy. So 36 times that's 36x cubed. 36 times 19 over 9. So 9 into 30, so 36 times that. Multiply this by 36. 9 into 30, that's 4. 4 times 19, that's 76 x squared. 36 times a quarter. That's 9x. And 36 times 1/9, that's minus 4. Alright? So this should be our solution for this section. So question 3, that's a trig proof. Show that sec squared theta is equal to cosec theta over cosec theta minus sin theta. So we can begin from the terms that has a lot of terms here. So the side that has more terms, or we can start what we said, RHS, the right hand side is equal to cosec theta. Now, what is cosec theta? So let me just put this, so cosec theta, and just for clarity, let me just put divide by the denominator, which is cosec theta minus sin theta. Now what is cosec? Alright, cosec, that's 1 over sin theta divided by here 1 over sin theta. Now cosec is 1 over sin, minus sin theta over 1, right? So that's the denominator there in the bracket there. Alright, so this becomes 1 over sin theta, and then what we could do is bring everything here in one common denominator. So that's sin theta. So we need both of these to have the same common denominator, sin theta. So I can multiply this by sin theta, which means I would have to multiply the top also by sin theta, right? So we end up with the common denominator. The numerator is now 1 minus sin times sin. That's sin squared theta. Good. So we end up with 1 over sin theta divided by, and 1 minus sin square. 1 minus sin square is the same as cos square. Remember the identity, cos square plus sin square equal to 1, which means 1 minus sin square is cos square. Alright? So this becomes 1 over sin theta times sin theta over cos square theta, and sin into itself, that's 1. So we are left with 1 over cos square theta, and remember 1 over cos is sec, so this is sec square theta, which is what the left hand side is. So therefore this proof was quite easily done. Alright, let's move on to part B, or part 2. Hence or otherwise, solve the equation cosec over cosec minus sine equal to 4/3. Now we just proved that all of this is sec squared theta. So we can replace that with sec squared theta. So sec squared theta is equal to 4/3. Now you recall that sec square is actually 1 over cos square. So 1 over cos square theta is equal to 4/3. And then we can reciprocate both sides, which means that cos square theta is equal to 3/4. Alright, so reciprocate both sides. We'll take the square root of both sides, root both sides, which means that cos theta is equal to plus or minus. So we square root the denominator, numerator, we get root 3. Square root the denominator, we get root 4 is positive, actually positive 2. So cos theta is plus or minus root 3 over 2. Which means that we have theta in all the quadrants, plus or minus between 0 and pi. We know from the common angles, cos 30 is actually root 3 over 2. Alright, so the common angle there is 30. Alright, so which is pi over 6. Alright, the theta, the common angle there is pi over 6. Alright. We need all the angles, we ask for all the angles between 0 and 2 pi. So pi over 6 is one of them. Now if you look at the quadrant, so this is 0. 90 degrees, 90 is what? Pi over 2. So 180 is pi. And this is 3 pi over 2, the 270, right? So to get the angle in the second quadrant, we'll subtract pi over 6 from pi. Alright, we should end up with 5 pi over 6. We add pi over 6, we should end up with 7 pi over 6. And then we subtract pi over 6 from, so 2 pi, we subtract pi over 6 from 2 pi, we end up with 11 pi over 6. So we should have solutions in all the quadrant. Alright. Part B, express the function sine theta plus cos theta in the form, so r sine theta plus alpha. So we're going to express sine theta plus cos theta in the form r into sine theta plus alpha, actually. Alright, so obviously we need to expand the right hand side. So expand, we end up with r into addition formula for sine. What is it now? Sine, right, okay, sine theta cos alpha plus, and then we alternate sine alpha cos theta. And remember, sine theta plus cos theta is equal to that. And then we can distribute the r. Distribute the r, we get r sine theta cos alpha plus r sine alpha cos theta. Now we can equate coefficients for sine theta and cos theta. So let's equate coefficients for both sine theta and cos theta. Coefficients. Now for the sine theta, on the left hand side, the coefficient here is 1 for the sine theta. On the right hand side here, for sine theta, the sine theta, the coefficient here is r cos alpha. Alright, on the left hand side, for cos theta, the coefficient here is 1. And on the left hand side, for cos theta, the coefficient here is r sine alpha. Alright? So we can divide both sides by each other. 1 divided by 1, that's 1. And r sine alpha divided by r cos alpha. R cancel r. So we're left with actually tan alpha. Alright, so tan alpha is equal to 1, which means therefore that alpha is tan inverse 1. Therefore alpha, or tan inverse 1, that's 45 degrees. Or pi over 4 radians multiplied by pi over 180 if you want to convert the degrees to radians. But since we're asked, it suggests that we should put the angle here in radians. Alright, so it means therefore, so we need r, we need the value of r. How can we get r? So we know that 1 equal r sine alpha. Alright, so how can we get r? We can alright, so from here we know, let's use, there's several ways to get r. Here we have 1 equal r cos alpha. So we can use this 1 equal to r cos 45 degrees, or cos pi over 4 radians. Alright? What's cos pi over 4? What's cos pi over 1 over root 2? So it's r times 1 over root 2. And if we multiply both sides by root 2, root 2 is equal to r. So hence r is equal to root 2. Alright, so therefore the function f theta can be written as, so now r is root 2. So that's root 2 sine theta plus alpha, and we have found alpha on the angle in the radians, so let me put it in the radians. Alpha is pi over 4 radians, which is equivalent to 45 degrees. Okay, let's see what else we're asked to find. Alright, hence find the maximum value of f and the smallest non-negative value of theta of which it occurs. So let's rewrite it. So f theta was equal to r, which is root 2 sine theta plus pi over 4. Alright? Now the maximum value, possible value for sine is 1. Alright, we should know that sine, the maximum value for sine theta is actually, it runs between 1 and negative 1. Alright? So f is at its maximum so f theta maximum value is actually root 2. Alright, so maximum value is actually root 2. Alright, since sine theta plus pi over 4 has to be 1, so the maximum value of f is root 2. And this occurs when sine theta plus pi over 4 is equal to 1. Alright? When sine theta plus pi over 4 is equal to 1, which means that theta plus pi over 4 is equal to sine inverse 1. Or sine inverse 1. Sine inverse 1 is actually 90 degrees, which is same thing as pi over 2. Sine inverse 1 is pi over 2, equivalent to 90 degrees, pi over 2 radians. Therefore, theta is pi over 2 minus pi over 4. And to subtract, we can get a common denominator by 2 times that. 2 times that. So it's actually 2 pi minus pi, that's 1 pi, over the common denominator here, 4. Right, next one. We're asked to prove that tan A plus B plus C is equal to all of that there on the right hand side. Let's try and do that. Okay, so one approach we can take is to use the associative property. So we can say, so tan A plus B, so tan A plus B plus C is equal to, and of course we can group the A plus B, so tan, and we can use a square bracket to separate it, put the A plus B together, the A and the B together, so A plus B plus C. Alright? So we're using the addition formula for tan, and let me just restate the addition formula. The addition formula says tan A plus B, let's restate it, is, so we add them, tan A plus tan B over, and this is in the, I think is on the formula sheet, is it? I'm not sure. 1 minus tan A tan B, alright? But so here A and the B are to, so it's tan the first term plus the second term over 1 minus tan, we take the products, right? So we're going to do that. Addition formula, so tan, and we're going to tan the A plus B first, so tan A plus B plus tan the C all over 1 minus tan, it's got to take the product of the numerator there, right? Times tan C. Good. Now, tan A plus B again can also be rewritten using the addition formula again. Apply to tan A plus B. Alright, so we end up with this together. So we end up with replacing tan A plus B with what here? So we end up with tan A plus tan B over 1 minus tan A tan B plus tan C, and I'm going to separate it now, alright? So this, alright, divide by 1 minus, let's divide by 1, let's separate the bracket here. So the second bracket would have the denominator, 1 minus, alright, same thing, alright, tan A plus tan B over 1 minus tan A tan B, alright. Tan A plus tan B over 1 minus tan A tan B, alright, times tan C. So all of this, alright, all of this will multiply by tan C. Alright, so times tan C. Alright, let's see how best we can simplify to get the expression on the right hand side now. Alright, so notice in the first bracket we're adding two fractions. So we can try to make this denominator be the same. 1 minus tan A tan B. Alright? So we can, so one common denominator, 1 minus tan A tan B. And we already have tan A plus tan B at the top there. Tan A plus tan B plus, and then we're multiplying this numerator by 1 minus tan A tan 1 minus tan A tan B, since, alright, so tan C times 1 minus tan A tan B. So that would be our numerator, alright, for this common LCM here. Divide by, and we're doing the exact same thing here. The LCM here is 1 minus tan A tan B. 1 minus tan A tan B. And we put this over 1. And we multiply the 1 by 1 minus tan A tan B also. So we multiply by 1 minus tan A tan B minus, and again, tan C times tan A plus tan B. So tan C times tan A times tan B. So let me actually expand it. Let me just put it here. So tan C into tan A plus tan B. Alright? So again, we have 1 minus tan A tan B. Let's expand. So expand now, we actually have tan A plus tan B. Expand the bracket. We have plus tan C minus tan C, tan A, tan B. So I'm putting it in order. Tan A, tan B, tan C. Alright? Divide by, over here, we have 1 minus tan A, tan B. And if we expand, we'll get 1 minus tan A, tan B, minus tan A times tan C minus tan B times tan C. So minus tan A times tan C minus tan B times tan C. Alright? Got a space there. So, alright. Can we group anything now? That term. So we can reciprocate. So we end up with tan A plus tan B plus tan C minus tan A, tan B, tan C over that 1 minus tan A times tan B times, and we reciprocate. So here we would have now 1 minus tan A, tan B over, so what we have here now, over 1, we should put the numerator, so we have 1 minus tan A, tan B, tan A, tan B, minus tan A, tan C, minus tan B, tan C. Alright, and this will divide into itself. B equals to 1. So we end up with the final proof, which is tan A plus tan B plus tan C minus tan A, tan B, tan C over the denominator 1 minus tan A, tan B minus tan A, tan C minus tan B, tan C. Alright? Which is what we were asked to prove. Alright, that's what we were asked to prove. Alright, so this proof was quite easily done. Alright, let's get to question 4.